variables in double and triple integrals. We've actually already kind of done this. When we changed to cylindrical, polar, cylindrical, or spherical, polar was changing in double integral, spherical and cylindrical was changing coordinates in a triple integral. So we've already done that. And we talked a little bit visually about why we have to put the R in when we change to cylindrical, and why we need the what is it, rho squared sine phi when we change to spherical. Now we can actually calculate it using the Jacobian. You saw that in the videos, so we won't do that in here. But I just want to talk, we're going to look a little bit about what's going on, and then we'll do a problem where we do a change of variables. All right. So basically what we're doing is equivalent to U sub that you did back in Calc 1 and 2, right? The thing about U sub is it only was for a single variable. Now, if we want to change both variables at the same time, we need to think a little bit about what happens with the dA or the dV if we're in a double or triple integral respectively. And just like with U sub, what we're doing is we're trying to make the integral easier to do. Same thing here. We might be wanting to make the integrand easier to work with, or we might want to be making the limits easier to work with, or both. So basically, we take something in the XY domain and put it over into the UV domain. Now, the first one I want to talk about is actually just the relationship between the two. All right, so let's say that U is between 0 and 1, V is between 1 and 2. So this would be the transformation. So it's kind of like we've already done the substitution. How would we get back to the original region? What was the region we were transforming? Why was it so messy? All right. So we're going to kind of work backwards on this one. This isn't something, you're really going to do in the homework, but this is just to kind of get you to kind of see how the two things are related. So basically what's happening in general is we have to integrate over this region R. So we transform it over to this region S, which is a nice rectangle, right? And when it's a rectangle, we don't care about the order of the limits, they're all constants. So if we look at this region R, we can see this would not be fun to do in rectangular, because we have a different top and bottom than we do here, a different left and right. This is going to take at least two integrals, and we have a curved side here. So what I want to do is just talk about how the two are related so you can kind of see what's going on. And the first thing we're going to do is these are the transformations that map. These would be our substitutions, right? This is what we would put in for all our X's and Y's. Okay, well, we see where this ends up. How did it get there from here? So that's what I want to look at. So the first thing we're going to do is we're going to get the reverse of these transformations. So we got the transformations, X equals U plus V, and Y equals U over V. And what I want to do is solve these for U and V. Okay, so there's plenty of different ways to go about it. One thing we could do is I'm going to solve this one for U, right? So I can see there, if I multiply both sides by V, U equals Y times V, and I'm going to sub it into this U here. All right, so that would then give me YV plus V. That is something I can factor out the V on, right? So Y plus 1 times V. And remember, it was originally equal to X. So that's going to give me, dividing both sides by Y plus 1, V equals X over Y plus 1. All right. Well, if V is X over Y plus 1, that's another straight substitution in for this V. And that means this is going to look like XY over Y plus 1. Again, this isn't something you're going to do a lot of in the homework. Again, I want you to just see how the two go back and forth. All right. So again, we have some integral we're trying to calculate in terms of X and Y. But we say, hey, that region's a mess. So let's do this substitution with u and v. And what that does, it transforms this region to this region here. We're going the reverse to see how the two of them are related. Now, one of the things I want to show you here, there's two more things I want to show. One is how the points translate between the two. So we have 4 corner points here, right? And those are u comma v, so just like alphabetical order, just like x comma y. So we can see that we have a point at 0, 2. So these are the u comma v points. What else do we have? We have 0, 1. We have 1, 2, and 1, 1. Those are u comma v points. Well, we're going to translate those over into x, y points. There's nothing. Actually, there we go. UVs. So u plus v, we get 2, gamma, and then 0 over 2, 0. So that tells me that the point 0, 2 is getting transformed over here to 2, 0. So let's put those back the way they were. I don't know why I was second guessing. Okay, 0, 1. This is the u, this is the v, right? So 0 plus 1, we have 1. And once again, we're going to have 0 over 1, so 0. All right. Well, we see that point. And also notice the colors are corresponding. So these 2 points got mapped to these 2 points, and notice there's the black line between. Okay, 1, 2. What's it going to be in x, y? Using these transformations here. 3. And 3 and 1, comma 1/2. I got it right there. And last one, 1 comma 1 is 2, 1. Right. So this is going to be something we're going to do in another example, because this is normally what you do first is you transform all the corner points, because the corner points in one region will be corner points in the other region. Okay, so we've taken all 4 of these corners and transformed them over to these corners. Now, because of the coloring, we can kind of tell which line goes to which line. But I want to show you how you can see that exactly. And we've got we got 4 cases, and we'll color coordinate as much as we can. So first off, if we're going along this line here, well, notice that u is always equal to 0, right? So u equals 0. So if u equals 0, well, what does that do for our transformations? Well, y is going to be equal to 0, right? Which is a horizontal line at 0, and v goes from 1 to 2. V goes, x goes, and v is equal to x in this case, x goes from 1 to 2. Right? Because if v is, if u is 0, x is v. Okay, let's see. Let's stick with u. Do not have green. But the other option for u is u could be equal to 1. Right? So when u is equal to 1, that's putting us on this green line. And v is going to go from 1 to 2. Well, if u equals 1, this becomes x equals 1 plus v, or v equals x minus 1. U is equal to 1, v is equal to x minus 1. So this becomes y equals 1 over x minus 1. And that's why it's giving this curved shape. And again, it's only happening for, this is for, both of these are the same, right? This was for V in between 0 and 1. This was for V in between 0 and 1. Well, if V goes between 0 and 1, and X is 1 more than that, X is going to go between 2 and 3. So X from 2 to 3, we basically get this piece of the graph of 1 over 1 minus X. I'm sorry, X minus 1. Okay, and let's just finish this one off just because we've come this far. So we'll do the blue one. So notice if we're going on that blue line in the rectangle, that B is equal to 2. So if we have B is equal to 2, then we know that two things. We know that Y is going to be U over 2. And it's 2. And we also know that X equals 1 plus 2, or just 3. Oh, sorry, not 1 plus 2. I'm looking at the wrong one. U plus 2. That's better. And once again, this is something we would solve for U and plug into here. So that's going to be Y equals X minus 2 over 2. So something linear with a slope of a half and a y-intercept of -1. Now this is going on as U goes from 1 to, or sorry, it's 2, yeah, it goes from 0 to 4. Nope, sorry, U's going from 1 to 2. U's vertical. No, sorry, U is going from 0 to 1. So as U goes from 0 to 1, X is going from 2 to 3. Last one, just to make sure that they all match up. That one in red. In that case, V is equal to 1. We see that it's linear. It's going to be real similar to the one that we just did. X is going to equal U plus 1. And Y is going to equal U over 1, or just U. So solving this guy for X, we get X minus 1. So this is the line of Y equals X minus 1. And this is for U going from 0 to 1, which would make X go from 1 to 2. So that's the relationship between the two regions. Again, the reason we did this in reverse to just kind of start to be able to work back and forth between the two. But the reason we would do this is S is a much easier region to integrate over than R. Okay. So we're just going through that to kind of get the hang of how these two things translate. We're gonna, in a second here, we'll do a forward example of a double integral substitution. But questions about that before we go on? That's what we're doing. We're this is, again, remember, this is a double variable example of U substitution. And so what we're doing is we're mapping between two regions, one in the XY plane and one in the UV plane. Now, where this is going to take us, we down on the board, is, okay, we're going to be doing these substitutions. So when we do U sub, remember we solve for the D, we find the DU, and that helps us make our substitution. We have that same thing going on in double and triple integrals, but it's called the Jacobian. And so the Jacobian accounts for the stretching, the rotating that goes on between the two regions. So the Jacobian is what calculates the R when you go from rectangular to cylindrical. The Jacobian is what calculates the rho squared sine phi when you go from rectangular to spherical. That's what the Jacobian gives you, that little factor there that has to be part of your dA or your dV. Calculating the Jacobian, and we'll do one here in an example for a 2x2, is basically the result, is not the result, excuse me, the determinant of a 2x2 matrix that's made up of the partials. And this is what you guys saw in the video. dx du, dx dv, dy du, dy dv, and you do the determinant of that. Not difficult to do, not a formula I expect you to memorize, right? This is totally something that can go on a note card very easily. This goes both directions because we might want to go from UV back to XY. It's the same basic concept though. Now, let's talk about changing variables in a double integral. So what we'll do, and this is very similar to what we've already done. In fact, in a double integral, we've already done this with polar. You know, we would put in X, you know, X is our cosine theta, Y is our sine theta. Those would be our transformations on the function. And then this would be the R that we put in dr d theta. Okay, so we've already done this. We just haven't done it in a general sense. So we're going to do this example. This would be a little bit more like what you would see, the way you would handle these, what you see in the homework. We'll do one kind of like this one on the worksheet a little bit later. All right, so we've got an integral. We're given a region we have to integrate over. Actually, not the worst region we've ever seen, but this integrand is going to be a nightmare. So we're going to use the transformation that x equals u and y equals u plus v. See what our new region looks like and see if we can get this thing transformed over. So let's see first off what our region looks like in the UV plane and see if we do have actually an easier region. Okay. So let's take a look at our first set of limits. Y equals x plus 2 to y equals x plus 3, right? That's going from this line to this line. What's that doing in terms of u and v? Well, remember x equals u, right? What's that? Anything you jump off? So this is going to transform into u plus 2 because we know x equals u and y equals u plus v. Well, that's going to be equal to u plus v. Right? Because y is equal to u plus v, x is equal to u, so you plug the u in here, there's the u plus 2. And then instead of setting it equal to y, we set it equal to u plus v. And that results in v being 2. Similar, almost the exact same thing is going to happen here, right? U plus 3, well, that's equal to u plus v, and that leads to v equals 3. So this is what's going on with our region. If x is u, and notice what x was between 1 and 2, we know u is between 1 and 2, right? So u is between 1 and 2. Well, now we know v is going between 2 and 3. So our region is just a nice rectangle. Questions about that? Yeah. And we're not going to be coming up with the transformations we're using on our own. So I don't want you to worry about that part. You'll be given the substitutions. But yeah, it took our region that was this slanted rectangle, and now we have just a basic rectangle. All right. Now we got to do two more things to get our integral. Number one is we need the Jacobian. Number two is that we have to sub in our transformation for x and y, see what happens. And that would be, so the way these would be chosen is based off of, okay, well, what is it we're trying to simplify? Well, we want the x plus 2 and x plus 3 simplified. So, all right, can we do something in terms of u plus v? Then we also go into this and say, okay, well, what's going to make that easier to work with as well? So Jacobian. So we're going to have dx du, dx dv, yep. And then dy du, dy dv. So we'll be finding the determinant of that 2x2 matrix. These actually don't work out too bad. dx du is 1. Dx dv is 0. dy du is 1 and dy dv is 1. Determinant of a 2x2 matrix, we briefly touched on this. What was it, back in cross product, but we haven't talked a lot about it. Basically, it's the product of these two minus the product of these two. I always thought it kind of looks like a fish, like a goldfish. That's how I've always remembered it. So what we end up with is 1 times 1 minus 0 times 1. So pretty simple Jacobian for this one. It just comes out to be 1. So not the most interesting Jacobian we could get, because even if we had forgotten to do it, it wouldn't have affected our integral. But you do need to calculate it because it's obviously no guarantee it's going to be 1. In fact, the one you guys are going to do, it doesn't come out to be 1. Okay, so that's the Jacobian. Now, obviously, if it's a 3x3, there's a little bit more work to the determinant. But again, you can use a formula sheet for that if you don't want to have to worry about the determinant of a 3x3. Okay, so we already know the order probably isn't going to matter, but let's take a look at what the new integrand looks like first before we make that determination. So that means we're replacing all the x's with u's and all the y's with u plus v's. So we are going to have square root of u times u plus v minus u squared. What's that? Did I forget something?
I just heard you say it's the square root, right? It's asking me to 1 over. You were standing right there. So
oh, sorry. Yeah. For now, let's put the 1 over. Because we don't have an order yet, I haven't put anything here. Let's just call it dA, and let's simplify this. Yeah, let's stand right in front of it. Okay. So what's going to happen? We're going to distribute this u. That gives us a u squared. Those u squareds are going to very nicely cancel. And we're basically just going to end up with the product uv. So 1 over the square root of uv. The order is not going to matter on this one because, we can do u first or v first. Basically, we've got 1 over square root of u times 1 over square root of v. So let's just say 1 to 2. So we'll do du and 2 to 3 dv. And again, remember, this is a product. You can break up a product over square roots. So we're not going to do this one right now. We've had plenty of practice calculating double integrals, but we would rewrite this as 1 over square root of u times 1 over square root of v, or u to the negative 1/2 times v to the negative 1/2. and one's a constant when we're integrating the other. So the integral actually wouldn't be very bad at all. So that's what we've done. And one thing I want to point out, we've talked about it a little bit with U substitution in here. And if you've had U substitution with me before, I always talk about it. With U substitution, I always mention one of the options is changing the limits so you don't have to sub back. With this, changing the limits is part of what we do, so we don't have to sub back. Like you might with U substitution, we just go from here on out to get a final answer. Questions about that one? Like I said, we're going to do one on the worksheet. That'll be kind of like this one in this forward way to give you a little bit of practice with it. Okay. Last thing I'll mention about this section. Well, first off, we're not going to do that example. You saw this in the video. If you do this with polar, you get R, and that's where that R comes from when we convert from rectangular to polar. For a Jacobian of a 3 by 3, it's Jacobian of a triple integral. You have to do the determinant of a 3 by 3 matrix. This is the same as what you're dealing with the cross product. So I'm not going to go and try and get you to memorize the formula for the determinant of a 3 by 3 matrix in here, because we're not going to do a whole bunch of triple integrals. But if you do this with the transformations for going from rectangular to spherical, you would get rho squared sine phi. And that's what you saw in that second video for today. So we're mostly just going to focus on doing it with double integrals. So I don't want you to worry too much about this. So, if you want to mess around with some triple integrals and do the determinant, you could use Wolfram alpha or to do your determinant, or, just kind of look up the formula for it. Probably not on a substitution, although you may decide to do a substitution. That would be up to you. But if you think about, the question was, would it be a take-home problem? Well, the reason we need substitution is because we have a hard to calculate triple integral. But if you can calculate it with Wolfram alpha, you might not need to do the substitution anyways. You might. I mean, there might be some that are, there are some that are undoable in rectangular that when you transform can be done. But I won't give you one of those. So I didn't want to spend a ton of time on this section because we're not doing a ton of stuff with it. Like I said, you've already done most of the substitutions already by having done cylindrical, polar, and spherical. But we wanted to look at it because I wanted you to see the Jacobian. Excuse me. Depending on what math class you're taking next, you might see the Jacobian again, because it is kind of thought of as a rotational or transformational matrix. Because like I said, as we go from one region to the other, that's what accounts for that shifting. So one of the things you can do with the Jacobian is morphing, right? If you think about taking one shape and morphing it into another shape, Jacobian accounts for that movement. What's that? Pretty much. Okay, so that ends module 4. So we are going on into vector calculus. And, it is a little bit of switching gears because, we're ending one chapter at the same time we're starting another. But I think you'll like this first section in this module It's